thank you for inviting me here. I think last time when I listened to Nimish, it was actually great to see people in the audience. Maybe you can also do me a favor and show people who are there. This will be kind of closer to the real-time experience. Can you hear me? Confusing. Hopefully.
Yes, sir, we can hear you.
Yes.
Okay. Anyway, I'd like to thank you for inviting me here. I'm sorry I couldn't make it in person. I very much wanted to congratulate Professor Dani, his wonderful anniversary, and wish him good health and more papers. So if this is if there is one sentence to express the contents of this talk, this will be the birthday wish to Professor Dani. And let me start. So this is joint work with Shah Mirzadeh, who actually is here on Zoom somewhere. If something goes wrong, feel free to correct me. I hope to do my best to convey what we did. And let me start with some basic setup. That's not what I wanted. So I'll talk about maybe something related to general situation in dynamics. We start with some metric space, which I'll call X. It has a probability measure of full support. And then there is dynamics. So you have some set of maps. Maybe it's a group or a semi-group. I call it F. And then I also choose a set U, which will play a role here. And I define what I'll call EFU. This will be a set of points in X, such that if you consider their trajectories, you go like this and like this and like this, and maybe like this, and then you never reach U. So the closure of the orbit is disjoint from U. Okay, so it's a set of points in X whose F orbits escape U. So hence the set E. And then one observation is that if this F is a group or a semi-group, which acts ergodically on this probability space, then this exceptional set has measure 0. All right. Now, let me give two examples. The first one, both of them are extremely elementary. So the first one will be the rotation of the circle. You start your axis, the circle, and then you rotate by alpha, and alpha is not rational. Then all orbits are dense. So for any non-empty set, this escaping set EFZ, let's say if U is just single point, this is empty. So there is nothing to worry about. So this is in purple, and then in blue I have another map, which I can maybe graph like this. So this S1 will be the unit interval, and this is a graph. And multiply by 2 mod 1. And then this set is very easy to describe using symbolic dynamics, and one knows that it's quite big. For example, it has full Hausdorff dimension, or you could write it like this. If you look at, so this is your circle, and your yes.
Question: you are denoting EFZ, but earlier Z was a open set.
No, not necessarily. Non-empty subset.
Non-empty subset.
Yeah, we can. I mean, it can be open. Most of the time, it will be open. In this picture, it is open, but nothing stops me from just having one point in this set. Then it will be the set of points whose closures does not contain this point.
Okay, the closure. Okay, sorry.
Is that clear? Yeah, I'm talking about the closure. If U is open, then you don't have to take the closure. Okay, so this will be the set of points such that if you have this binary sequence, you shift. For example, if z is let's take z is equal to 0, then you have it right here, and then it will be the set of binary sequences which do not contain arbitrary long stretches of zeros. Then it will escape, the orbit will escape this point. And it's very easy symbolic description. And, in other words, if you take a very small interval around 0 and call it u, this u will be now the ball centered at 0 of radius r is very small, then the dimension of this escaping set becomes closer and closer to 1.
I have a small doubt when you are talking of EFU and you want the orbits to not touch U, that means you are keeping yourself away from transitive systems?
Well, in some sense, you're right. So in the example 1, the system is transitive and then nothing escapes U.
Okay.
In example 2, the system is not transitive. It's ergodic, but still there are many non-trivial invariant sets. So in a sense, this is the subject of my talk. The systems which are not minimal, because in minimal systems, nothing escapes anything.
Okay.
Is that clear?
Yeah, thanks.
So this expanding endomorphism of the circle is a good example. It's an ergodic system, but there are many strange invariant sets. In particular, you can talk about points which do not come closer to something, to a small interval, and everything can be very well understood here in this example. For example, the Hausdorff dimension of this set is 1 minus some constant times r, and this constant can be explicitly computed. This is done in the papers of Bunimovich, Yurchenko, and then more generally by Ferguson and Polycott. My goal is not to talk about these systems, but switch to dynamics on homogeneous spaces, where things are more interesting, so to say, or maybe less interesting, I don't know. So I want to have the following setup. Feel free to interrupt me if you guys have any questions. So X will be G mod gamma, where G is a Lie group and gamma a lattice in G. Mu will be the G invariant probability measure. And F will be a semigroup, most often one parameter semigroup, acting on X by left translations. Okay, and now we have these two examples which are pretty close to homogeneous dynamics. In fact, the two examples give rise to two special cases: unipotent dynamics and partially hyperbolic dynamics. And the situation, you could see that the situations are very different here, and they are very different in general. So in unipotent dynamics, unipotent dynamics is much closer to the transitive case than partial hyperbolic dynamics. So in the purple situation, you have Ratner's theorem, you have a technique of Dani and Margulis, and in particular, it follows that the set of points x such that fx is not dense, let's say if f is a unipotent group or a unipotent semigroup, this set is contained in a countable union of proper submanifolds. Okay, so this EF, in other words, in this case, EF Z is maybe that's not this EF Z is small, informally speaking. Okay, so it's contained in the union of manifolds of positive codimension, and in the partially hyperbolic flows, the converse can happen. Because of this certain features of dynamics, in particular exponential expansion of unstable leaves, one can actually prove that the set of points which don't come close to, say, a fixed point has full Hausdorff dimension. and let me so because of this I'll concentrate on this case for my talk, and of course I have to go back to contributions of Dani because that's his birthday conference. So let me talk about history a little bit. This study of exceptional orbits actually was initiated by Dani in the 80s, and let me show one observation of Dani in this slide. So you look at the space X, which is the space of unimodular lattices in Rm plus n. So this is so X here is SL m plus n R modulo SL m plus n Z. Okay, and F is one parameter semigroup GR plus, where GT is given by this, expanding the first m components and contracting the last n components, and then the trajectory, and then you look at this certain lattices in this space, and the trajectory is bounded if and only if this matrix A, which you have in the top left corner, is badly approximable. So it's not really important what this definition is. What is important is that this was observed by Dani, and it gives rise to what we later called Dani correspondence in a paper with Margulis. This was the first instance of it, and it was important. Okay, so the definition is that basically AQ plus P, where Q is an integer, P is an integer, and AQ plus P is not too small. It is bounded from below by a constant divided by norm of Q to this critical exponent n over m. And it was important because of a result of Schmidt, who proved that the badly approximable matrices form winning set. Maybe it will be mentioned in other talks of this conference, I don't know. This and the fact that the set UA is form expanding hemispherical or unstable hemispherical subgroup of G relative to this semigroup enabled Dani to conclude that the set EF infinity has full Hausdorff dimension. So what is EF infinity? I mean, you can basically stretch the definition a little bit. And if this space X is not compact, attach infinity here, just compactify. And then EF infinity will be the set of points which stay away from infinity. So the orbits, the trajectories are bounded. Okay, so you can consider also this type of exceptional orbits if you have a non-compact space. And then Dani also modified Schmidt's argument to prove a similar statement for quotients of rank 1 Lie groups. So you have a lot of exceptional trajectories, a lot of bounded trajectories, and there is some history to this problem. The full statement for arbitrary Lie groups was conjectured by Margulis in his ICM address, and then we wrote a paper in '96 settling this. Later I proved that even if you have so if this is your X, which is G mod gamma, and you take one point Z and you want to avoid it by a partially hyperbolic flow, then the set of exceptional orbits also has full dimension. Okay, so what does it mean? It means, let me just restate these results. It means that if you look at some family of compact subsets exhausting this X, then parameterized by epsilon, then dimension of this set of points escaping the complement goes to full dimension as epsilon goes to 0. And likewise, if so let me just draw two pictures here. Here you look at Q epsilon complement. This will be my U. And here my U will be balls of radius epsilon, and you want to consider orbits escaping this cusp neighborhood, or you want to consider orbits escaping this ball, and as epsilon goes to 0, the codimension goes to 0. Okay, and now the question that I want to address is what happens to these sets for fixed epsilon? So now I really want to consider this little open set and see what happens. And here is the question that I want to address. And this question comes from Maryam Mirzakhani, who asked this to Alex Eskin, and Alex asked me. And I said, I don't know, that I didn't know. And then we started working on it. So the question is as follows. Suppose you have ergodic action, and you take U, which is open and non-empty. So this is the situation. You take this U right here. Is it true that the set of points with orbits escaping U necessarily has less than full dimension? So would it be possible to have full dimension this set? Right? In other words, you have this limit. You have this sets E F something where this something shrinks, and then dimensions go up to full. But maybe at some point you do have full dimension already. Why not? This was the question of Maryam, and this is a conjecture that it doesn't happen. In other words, if you have an action on homogeneous space X, then either the set of exceptional points has positive measure, for example, if it's not ergodic, or codimension is strictly positive. In other words, we cannot have a proper closed F-invariant subset of full closed dimension. This is the question which somehow is motivated by kind of inverting what Dani was working on, having something closer and closer to full dimension. Okay, and just a minor remark that we'll also consider, in addition to these sets E of U, I want to consider the sets E tilde of U. Those will be a set of points which eventually, I don't know why it doesn't eventually escape U. Okay, so in other words, you again have this situation. This is X. You have your little hole, and then your orbits are allowed to cross maybe a few times, maybe like this, and then it will go away and never comes back. Okay, so you can look about this, and it's not very different from the previous setting. You can easily see that the dimension drop conjecture stated above implies the corresponding statements for the bigger set. Okay, so we also aim to understand the fact that if you are allowed to do it for finite time and then stop doing it, you still need to have less than full Hausdorff dimensions. Just the argument involving countable union of sets. And another remark is that this conjecture is interesting only if F is partially hyperbolic. Again, we talked about unipotent dynamics. In the unipotent dynamics, we have a very serious drop of dimension. It drops not just by epsilon, but by an integer. So it makes sense to look at partially hyperbolic world. And then it is interesting only if the space is not compact. So if the space is compact, then somehow things are well understood. And essentially, this argument is due to Manfred Einsiedler and Elon Lindenstrauss, and we wrote it down in the paper with Barak Weiss. about 10 years ago. So basically, there are some ingredients here which I mentioned only briefly: the relation between Hausdorff dimension and entropy, variational principle, and uniqueness of measure of maximal entropy. So basically, roughly speaking, if you have this set U, which you want to avoid, and since the space is compact, you can consider you can put a measure on this invariant set, and because if you assume that the Hausdorff dimension is full, it gives you maximal entropy, but or actually you start with topological entropy, and then using variational principle you get to measure theoretic entropy, and by the uniqueness of measure of maximal entropy, it has to be a Lebesgue measure or Haar measure, but this U is not there, so there is a contradiction. But if X is not compact, this argument doesn't work, and this is what I'll be talking about in this talk, because again, you start doing this, you have this U that you want to avoid, and you're putting some invariant measure, and then it can go away, and you don't know what happens. Okay, so this actually was overcome in the case when the rank of G is equal to 1 by Ansidler, Kadyrov, and Paul. And what I want to talk about is the general proof, which is different from their proof. Okay, any questions? So before trying to answer this question, let me ask another question. Namely, if the dimension is less than full, suppose we can prove it, maybe we can even do it effectively. So estimate somehow the dimension, because clearly the smaller is U, maybe the smaller is this codimension. So there should be some argument, and this question is interesting even when X is compact. And there is a rather simple idea how to do it, which is one of the ingredients of today's talk. It was first tested in my paper with Ryan Broderick in 2015, and then in the work with Shahriar. So let me show a little picture. So suppose I have my homogeneous space X, and I look at what I'll call unstable hemispherical subgroup, and apply this group GT. And what I want to use is the fact that when you translate these red leaves, the result becomes equidistributed. And in fact, you can sometimes explicitly estimate the rate of equidistribution. Okay, I think it was already mentioned in Nimish's talk and maybe other things, other times. So again, here you have this U, and when you translate it by large T, you are going to have something going through everything. In particular, you have to touch this U. Okay, and then what I want to do is I want to divide this guy into a bunch of short intervals, so that when you translate, these intervals are roughly of the same size as before, and so in particular, some of them will touch you and some of them will not touch you. And let me just completely get rid of those which are inside U. And because of equidistribution, there will be some non-zero proportion of these guys that I can throw away. And then you start, you look at each of the intervals which are left, for example, this one, and you do the same. You also expand, and again you have the expansion which will go through U, and you keep doing it, and you get a Cantor set, which some kind of Cantor set, which has positive codimension because you throw away some proportion of intervals. So it's an extremely simple idea, and it makes it possible to get some estimate. When you have to play with these parameters, so this set T that you choose, right? So you choose a fixed T, and you want this T to be big enough because you want to apply the rate of mixing, and you have to wait until you have mixing. But you want this T to be not big enough, because if this T is very big, if you have a lot of intervals, then the dimension estimate will not be too good. Okay, and also you want this estimate applied uniformly, and that's why compactness is important. So let me, essentially this is the whole proof for you, but let me give you a little more detail. So you start with F, which is a one parameter subsemigroup of G, which you assume is diagonalizable. You let H be the unstable hemispherical subgroup. This is the gives you the foliation which gets expanded by the action. And more generally, I want to fix a subgroup of H normalized by F. Okay, so sometimes it makes sense to consider. So maybe here you have H, which is expanded by the action, but in application, sometimes you need to stick to a smaller subgroup, which I will call P. Okay, and nu will be hard measure on P normalized so that unit ball has measure 1, and what will play a role in my talk is the operator IFT, which is defined as follows. You start by choosing some function on this P, then you expand it by GT. So you get this stretch, and then you have a test function psi, and you average this psi over this stretch. So that's the definition. Okay, and this will play with these integral operators during the talk. And another technical ingredient is the injectivity radius, which will be important. So if you have my homogeneous space X, and this is the group G, and this is the projection pi sub X, which sends identity element to X, then you are interested in this biggest R such that the projection is injective. So when you get from here to here, you don't glue points together by this pi X. And R0 will be the injectivity radius of a point or of a set. It is positive if and only if this set is bounded. Okay, so as you go to the cusp, you'll get smaller and smaller injectivity radii. And so here's a very confusing, probably, definition. I'll say that the subgroup P has effective equidistribution properties with respect to the flow if there exists some constant, A, B, lambda, and L, such that whenever T is big enough, and this big enough T is in terms of injectivity radius of X. For example, if the space is compact, you just need to have uniform bound. Then you're going to do the following. You start with this X, and then you have a function f on P, which gives you something like this, and the function psi on X, which is a test function, and then you apply this integral operator. So you translate by t, and now you have this long curve that you integrate this psi, and this is very, very close to the product of integrals of f and psi. Okay, so in other words, this translates, get equidistributed with exponential rate, and not only you have exponential rate, you have some constant depending on the functions psi and f. So it's not really important how this constant is written, but this is what we can prove, because one thing that one can show is that if the flow is exponentially mixing, it implies the effective equidistribution property for P being the unstable hemispherical subgroup. Okay, so this is a computation which was essentially done in my paper with Margulis long time ago, and then it also showed up later, and it also can be proved for proper subgroups of H. Anyway, let's just treat it as an axiom. What is important is that you cannot really hope to get it for all T if the space is not compact. So for all T big enough independent of X. So you have to if you have your X very far in the cusp, then you have to wait a long time until you start mixing. Okay. And now I'm almost ready to state the theorem. I just need one more piece of notation. If U is an open set, I'll talk about sigma R of U, and this will be the inner core. Let me draw it using yellow. Okay, so this will be the set of axes points which are away from the boundary of U. Okay, and so it is this, and then I'll also talk about something. I don't know what. Bigger set, and this will be the R neighborhood of U. Okay, so the set of points which are most R away from this U. And now this is the first theorem that we proved under this quite strong assumption that the complement of U is compact. Okay, so then we are able to prove that so here's the situation. You have our X, and you take point X, and then you look at the leaf of this subgroup P, which I assume to have effective equidistribution property with respect to the flow, and then you flow by GT, and you want to stay away with U, stay away from U, and my U is something like this, or maybe another situation is that when X is compact, then of course I can take anything I want. I can take a small ball, but if X is not compact, I have to grab the cusp. So then if you take this U, and for every small enough R, you have the following estimate for the codimension of the set of G and P, such that Gx belongs to this exceptional set. Okay, so this is a very strange inequality, because here you have no R, and here you have this extra R. So the way you use it, and you choose R which works better for you. Okay, for example, if x is, let's say, if x is compact and u is the ball of radius r, then in the numerator you have the r inner core of u. It is basically, it's close to the measure of u, and in the bottom you have so basically you choose r a little bit, say half r, replace r with r over 2, and then you get an estimate like this. Okay, so this is your x, and this is your u, and this is an inner core, which will be quite, so you can choose this extra r, which I denoted by the same letter to make it a bit more confusing. But I hope it's clear that you get this an estimate like this. And by the way, because of the deficiency of our method, because we have to play and optimize certain parameters, conjecturally, this is not needed. I mean, it shouldn't be there. So the right estimate really should be r to power dimension x, but we can only get it like this. And of course, we can, this is a foliated estimate, but we can get the same estimate for the global codimension. And then, since it's a Dani's birthday conference, you can actually have de Fontane consequence. And for this, I'm talking about weighted de Fontane approximation. So here I'm talking about I, which is a set of weights, and another j, which is another set of weights, j n, such that the sum of ik and the sum of jl is equal to 1. And you're talking about the set of weighted Bedley approximable matrices with certain with fixed lower bound given by this C, and this by the weighted version of Dani's correspondence gives rise to an open set like this in the space of lattices, and your act by GT, which is a diagonal group where you have now e to I1t up to EIMT, and then e to minus J1t all the way up to e to minus JNT. And what is important here is that you have an example where you have expanding hemispherical subgroup with respect to this action, and the group that I'm talking about is strictly smaller, but still you can prove effective equidistribution property for this P. This is a result of essentially a result of our paper with Margulis. And again, conjecturally, you need to somehow get rid of this log 1 over C for equal weights. This was actually done by David Simmons. Okay, so I'm getting to the main subject of my talk, namely what to do if the complement is not compact. Because unfortunately, this nice scheme is not working well. So now you suppose you have some cusp, and you start by taking a piece of p orbit, and then you apply this GT, and it gets it still gets equidistributed, but then part of it is quite far away. Okay, and when you apply it again, it gets maybe even further away and even further away. And then your mixing estimates become much harder to use. Okay, so and let me remind you that the whole point was to escape some piece of this space X, and the further you are, the more likely you are to escape it. Okay, so you have to come back. And this nice scheme of using exponential mixing every time works for some cases, but sometimes it breaks down. And let me give you an example before talking about what we can prove. Again, I start with the same situation. X will be the space of lattices in Rm plus n. GT will be this nice subgroup which expands the first m components and contracts the last n components. And the question is, can you prove that for any non-empty open U, this set of points escaping U has positive Hausdorff codimensions? And this is again like exactly the non-compact situation. And I want U to be rather small. And it's probably not hard to guess that an affirmative answer would have some consequences for the Fontaine approximation. The reason is that since it's a conference dedicated to Dani, it has to be like that. There's no other way. And indeed, let me explain why this is the case. And I want to throw in another definition from the Fontaine approximation, which was already mentioned by Anish 2 days ago. You say that A, which is a system of linear forms, is C directly improvable for some fixed C. If you have this variation of Dirichlet's theorem, where instead of n to power minus n over m, you put a little c here. And for all sufficiently large n, you are required to have solutions. Okay, and DI-Mn of C will be the set of C directly improvable matrices. So what is known, first of all, is Dirichlet's theorem gives you C equal to 1. Then everything is fine. But then Davenport and Schmidt actually proved that if you replace this 1 by C strictly less than 1, you get Lebesgue measure 0. And they also proved that it still is a big set, because the union of these guys over all C less than 1 contains Bentley approximable matrices. So in particular, dimension goes to Mn as C goes to 1. This is the same situation as we had in dynamics, and you can ask the same question. Can you have full dimension of these directly improvable guys for some M and N? Maybe you can, I don't know. But in fact, one does know, and the reason is, again, Dani's correspondence with dynamics. So let me show a proposition which is contained in our paper with Barak Weiss, but essentially it is more or less in Dani's paper from 1985. Namely, if you fix C strictly less than 1, there exists a non-empty open subset, which I call U sub C of the space of lattices. And for those who understand what's going on, it's a neighborhood of the critical locus of the supremum norm. So next week, I think we'll have the talk of Anurag Rao, who will explain more about it. But maybe I can try to draw a picture. So this will be my set X. And now I have this set U sub C, which is actually quite complicated. It has some rather complicated structure, but somehow A is directly improvable with this parameter C, if and only if you start with this leaf given by U sub A applied to the standard lattice, and then you start flowing by GT, then you'll eventually miss this green set. Okay, so this is basically the reason why you have Lebesgue measure 0. The flow is ergodic, and so those who miss it are negligible. Okay, and the fact that actually there exist a lot of them which miss it comes from the second fact, that bounded orbits have to be away from this critical locus. But what if the orbit is unbound? Maybe you have a lot of unbounded orbits which are also away, and maybe you even have full dimension. This is the question. So it turns out that the answer is that you always have less than full dimension. We have this affirmative solution to dimension dot conjecture, which we did with Shahriar a couple of years ago. And then you can actually use it plus some work that we did in the paper with Shucheng Yu and Andreas Strömbergsen that I think Shucheng will talk about later. So you can actually have a very explicit estimate for codimension of this set for some explicit constants A and B. It's not optimal, probably, but at least it's there. So, so this is one thing that this solution of dimension drop conjecture can get. This was one of the motivations for doing this, apart from the fact that Maryam asked this question. And now, what can we do in this non-compact case? So I'm going to give you a general statement, which I'll need to prepare a little bit. So maybe it will take 5 minutes to get us to the point where I can state the main theorem. I need some more terminology, and this terminology goes by the name of height functions, which were already mentioned by Nimish and maybe by other people. And this technique essentially is designed to describe the structure of the space at infinity. Okay, so in general, if you have this X, which is not compact, you say you pick a function U, continuous function, positive continuous function on X, and you say that it's a height function if it is proper and regular. And proper means that if you look at its level sets, then they just go to infinity. So you cannot have a situation where this U actually blows up at a finite part of the space, right? So this is not allowed. And regularity means that if you perturb the space, if you perturb the point, then this U is not going to change drastically. So in other words, the picture that you have this level set, and then this type of level set where you are changing point a little bit and the function changes by a lot, this is also not allowed. So you have some kind of regular picture which describes the structure of the space at infinity. And then the main axiom is so-called Margulis inequality. With respect to some operator sending continuous functions to continuous functions, you say that this U satisfies such an equality if you, whenever you apply this operator to U, IU at a point X will not be greater than C times U of X plus D. And this C and D are parameters of this inequality. And these functions are called Margulis functions. So the height functions satisfying this inequality are called Margulis functions. There is a very nice survey by Alex Eskin and Shahar Moses in the Margulis conference volume, Margulis birthday volume, which we just published. And of course, my I will be I of t, which I described before. In fact, for F, I'll just take a characteristic function of unit ball and P. So what will happen again is you start, you take this unit ball, you attach it to a point X, and then you flow by GT, and you get some stretch, and then you integrate or you average these values of u along this trajectory. And Margulis inequality says that this average is not going to be, is going to be bounded by the value of u at x times some constant which is still less than 1. So in other words, if you start with x, x being somewhere here, okay, maybe you don't have to do this. So if you start with x somewhere here, and maybe your translate is like this. Now this is prohibited by Margulis inequality. You cannot have substantial part of the trajectory which is very, very far away, so that the values of u are big. That's the meaning of this inequality. Okay, so again, this is not allowed. And this is my definition. The subgroup P, so P shows up here. Remember, this is P times X. It has effective non-divergence property abbreviated by E and dP with respect to the flow. If there exists a constant C0, strictly less than 1, and T0, such that for any t bigger than T0, you can find a corresponding height function. You can have a family of height functions. In fact, sometimes you can just stick with one height function, but sometimes it's difficult. But what is important is that each of these functions ut satisfy Margulis inequality with respect to this T0, which is fixed, and dt, which we don't care. So this additive parameter can be different, but you need to have the same C0 strictly less than 1. Okay, so in other words, if you take this u and you integrate it with respect to the measure over the translate, you're going to have a bound C0. Sorry, this is a mistake. This should be u sub t, of course. Utx plus dt. Okay, and this whole thing comes from the papers of the paper of about quantitative Oppenheim conjecture by Eskin, Margulis, and Moses. And then recently there are many examples essentially generalizing the construction there by Guan Shi, by Rodriguez, Hertz, and Wang, and something we did with Kadyrov, Lindenstrauss, and Margulis that I'll mention later, and also something we did with Shakriar. So in many situations you can construct these height functions. Okay, we can talk about specific situations, but the point is that you can treat it as an axiom, and then you are lucky to have the final result. So the theorem now can be stated in a very concise way. Suppose this P has these two properties, effective distribution and effective non-divergence with respect to the flow, then dimension drop conjecture is okay. Okay, so in other words, you have dimension drop conjecture, in fact, along leaves of P. So the dimension drops at every leaf. Okay, and here I stated it in an ineffective way. You can effectivize it a little bit. And I wasn't sure if I have enough time for this, but this can be done. So you can say that you have property ENTP plus if in addition you know that these functions grow uniformly fast enough where you measured it towards the injectivity ratings. Okay, so you compare the growth of this u with the radius, the smallest ball that you can put there. Okay, and you have this R0 of x to power minus alpha for some fixed alpha. So if you if you can relate this height function to injectivity radius, basically, then you can even do this quantitatively. Let me. So this is the uniform bound for this set where the dimension drops, and the drop is bounded from below by the measure of u times this log factor, and this log factor involves theta u. So here basically I get rid of this additional parameter r, and the idea is that if you have an open set U, you find a smaller set. Use the step. So this is the inner core, with parameter 4r, and you want the biggest r such that this measure is at least a half. Okay, and this you call theta u, and this theta u also appears here. So it's not really important. The important thing is that it can be somehow estimated effectively. In any case, it's not the optimal estimate, but it's easy to see that if u is the ball of radius r, then both of these parameters, both the measure and the theta u, are polynomial in r. So we're getting again the same estimate of type r to power dimension x over log 1 over r. Okay, so I think my time is almost up, modulo the fact that I started 5 minutes late. So maybe I can use these 5 minutes for the last 1 or 2 slides, just to explain how this is actually proved. And to prove it, one combines the first theorem. So the first theorem was about effective equidistribution with a method from our paper with Shirali Kadyrev, London Strauss, and Gregory Margulis. And the goal of that paper was to control trajectories which diverge on average. Okay, so in other words, suppose you have you want to study trajectories which do the following: you apply GT, and they go further and further away. Okay, well then, if you know that your Margulis inequality is satisfied, then at every stage you basically have quite few, I mean, not a lot, not a big part of this translate, which is far away. And at this stage, you also have not a very big part of this translate, which is far away. Most of them will come back. And in other words, if you have a divergent of on average trajectory, then this iterates will be far away, and then using Margulis inequality plus the regularity of U, we show that the set of those x's can be effectively covered by a relatively small number of balls. So there is a certain inductive technique which was used there, and it's basically the modification of the same technique which we found possible to use in this setup. So maybe as a last picture to show, again, you have my non-compact space X, and this is the set U that you want to escape, and then you start with a little piece of p orbit attached to X. You apply GT, and you are in the same situation. You have a very long stretch, and some of it is far away and some of it is close, and then you want to break it into little pieces and apply the same technique for to each piece, and then it depends on whether or not you are far or not so far. So you choose a rather big compact subset Q sub t. So I said super level set, but this is a mistake. So it should be sub-level set. So the complement of Qt is super level set. Okay, and then there are two cases. Well, there is an inductive construction, and in each stage of the induction, you choose. I mean, you have two possibilities. Either you are outside of this Qt or you are in Qt. And if you are in Qt, you apply this effective IQ distribution, which is uniform in this compact set, and you are able to throw away some pieces which land in U. And if you are outside, then you apply Margulis inequality, and you also win. You can you cover this set by some number of boxes, which happens to be small. So basically, this is the argument in a nutshell, and it's very rough sketch because there are lots of technical details. There are boundary effects. There's a need to smoothen the functions somehow. Replace characteristics functions with smooth functions, you lose something there. And also the expansion is not conformal, so you have to work with Bowen boxes, with these rectangles that you then cover by boxes. There is a lot of technical stuff, but at the end, somehow it works out that this dimension drop can be established. So I guess now my time is really up. So well, thank you for invitation and for your attention. I want to show Shahriar's picture. He is the main collaborator here, and also Andreas and Shucheng were mentioned as the people who derive something interesting from this result. So I thank them too. And of course, the last slide goes to Professor Dani, again wishing many more productive years ahead and good health and happy birthday. Thank you.
Any questions, comments? If there is no questions, please let's thanks.
May I ask a question?
Yeah, please go ahead.
Hi, Dmitry.
Yes.
So do you have you considered the intersection of this bad C with different weight and house of dimension?
Well, that's a very good question. So so I think we can do it, but what it means is that we need to have to construct this height function, which satisfies this Margulis inequality with respect to this flow which has different weights. And in a sense, so I believe this can be done, but it's just basically it means going through the procedure in our paper with Aravinda, Strauss, and Margulis in a weighted setting. This is something close to it was done by Solan, Tamam, and Shi in their paper where they have estimates for Hausdorff dimension of weighted divergent trajectories. So the short answer is that I think it is possible to do, but we haven't done it. Maybe later.
Do you have some expected result, like the Hausdorff dimension could be smaller than if you take the intersection?
Yeah, that's a good question. I really the problem with our estimates is that we know that they're not optimal. That the truth is somewhere, and we cannot get close to it. So it's hard to make conjectures about this weighted situation.
Thank you.
Maybe something can be done.
Thank you.
Any more questions? Comments? Okay, if there is no questions further, let's thanks Professor Kleinbock again. Yeah.
Okay, thank you for hosting me. Sorry I wasn't able to be there in the room. Have a great conference.